Today we are going to see Introduction to Computer Control of Processes, Part 11. Introduction to Computer Control of Processes, Part 11, 16th webinar. Today we are going to see Dahlin's method once again, and then we are going to see the difference between Dahlin's method and deadbeat method. Then the ringing effect. Yesterday, I think we started that ringing. Today, we'll see that ringing. Then we'll see how to remove ringing, elimination of ringing, that and all we are going to see. Then we'll see some simulations in MATLAB. Now, Dahlin's method. What is the assumption we made while designing a deadbeat controller? In deadbeat controller, we made the assumption that the response is also a step function. Response also a step function after one sampling period. After one sampling period. That's why the response will be too oscillatory. The response will be too oscillatory, and large overshoots will be there because we are forcing the system to settle in one sampling period. That's why the controller will give a huge amount of control action within that first sampling period. So large overshoot will be there and large oscillations will be there in the deadbeat algorithm. That is the drawback of deadbeat algorithm, provided if mathematical model and process are not exactly matching. If you do process are not exactly matching. If you take a process that suppose you are taking 1 by 0.5 s plus 1 as a process, and for this you are designing the controller. This will be the system, this will be the model. If both are identical, then you won't get this type of large overshoots and oscillations. Because mathematically model and process are identical, that's why the simulation will perfectly work. Mathematics is perfect, that's why you won't get any overshoot and all. You will get the same exact response like this. That also we'll see today. If process and model, it's not possible to model a process exactly. Already we have seen that if you take a level process, if you obtain the if you take a mathematical model, if you take a level process, in that level process, we know that if you obtain the mathematical model by using first principle in level process, it's a first order process. If you see level alone, then it is a first order process. It is not so in practice. We cannot operate the level process alone. To measure level, we have to connect a level transmitter. If level transmitter also a first order process, then if you combine level process and level transmitter, then it becomes second order. Then the output of the level transmitter is given to the controller. Then controller gives some output based on the error. Then if controller is another first order, then the order becomes third order. If the controller output is given to if it is a digital controller, its output will be given to a DAC, and before that we have to see one more thing. ADC is there. The transmitter output is first order. Let us assume that it includes ADC also. If the controller output has digital output, then it should be given to a DAC. DAC has zero order hold. Then the order becomes 4. Then output of that zero order hold is given to valve. Order becomes 5. Suppose I to P is there. You convert the 420 milliamps into 3 to 15 psi. For that one, I to P is there. then the order becomes 5. The output of I to P is given to val. That becomes order of the system 6. So if you see that the order of the system is 6, it's very difficult to find the exact mathematical model. That's why always the mathematical model used for design of controller is approximate. If the mathematical model used to design the controller is approximate, then definitely there will be oscillations. If we are able to get the exact mathematical model of the process, then deadbeat controller is very good, very good. Then it knows the exact dynamics of the process. That's why it will generate a controller output so that the response will be settled within that one sampling period. But it's very difficult to get the model. We will model the level process in our lab as a first order model with the dead time. Because as order increases, you will get a transportation lag, you will get a dead time. That's why we are approximating the model, sixth order model, as if it is a first order with the dead time. That's why if you use a deadbeat controller, it will be large overshoot and oscillations, because it's not at all possible. It is impossible to obtain the exact mathematical model of the process. We'll get approximate model only. That's why there will be large overshoot and oscillations in the output. So in Dahlin's method, we are using that mathematical model to design the controller. In addition to that, we are specifying that response as first order with the time response. Like that, we are assuming. If you assume like that, then you won't get that much oscillation as we got in deadbeat. Now we will see that design. Here, the assumption made in the Dahlin's controller is first order, the response is first order with the dead time. The response is first order with the dead time. The dead time, this is assumed as theta. Here, you can notice that theta. The dead time it has is theta. This is theta. And the time constant we can select. So the time constant mu, you can select your time constant after this dead time, how much time to take 63.2% of final value that we will find, that is the mu, the design parameter. It is a first order response. That's why we have to multiply this by 1 by s. Therefore, the first order response, we are assuming that y of s equal to e power minus theta s upon mu s plus 1 multiplied by 1 by s. That is the assumption we made. If this is the assumption, then y of z equal to if you take the y of z for this denominator s multiplied by mu s plus 1, the numerator e power minus theta s. The dead time theta equal to k times sampling period. That's why z power minus k you are getting. This part is over. The remaining part 1 by s multiplied by mu s plus 1. So what you will get from the table, you can directly get this. In the table, you will get 1 minus z power minus 1, 1 minus e power minus a t, minus a sampling period t, z power minus 1. Here, if you bring this mu outside, what you will get is 1 by mu upon s multiplied by s plus 1 by mu. If you assume mu is a, so a by s multiplied by s plus a. For that, the formula is 1 minus e power minus at whole multiplied by z power minus 1 upon 1 minus z power minus 1, 1 minus e power minus a sampling period t z power minus 1. This is the from table we can write a response for this. So multiplied by dead time, that is z power minus k. Theta equal to actual dead time equal to TD plus 1 sampling period. Because of this minimum, we are taking this as 1 sampling period. If no dead time is there, that's why we have to assume that theta equal TD plus 1. So if you convert this into in terms of sampling period KT, approximately equal to slightly higher than this, you can select. So TD plus 1 approximated to KT, then you will get Z power minus K. So what is set point? This is for step input. Already we have seen that what we have seen here, the step input, unit step input. Therefore, y set point of Z 1 minus 1 by 1 minus Z power minus 1. Therefore, y of Z by y set point of Z, that 1 minus Z power minus 1 getting cancelled. If you multiply with that, this 1 minus Z power minus 1 getting cancelled. So what you are getting is, we divide this by the previous one, this term getting cancelled. Therefore, you are getting Z power minus k, 1 minus e power minus t by mu Z power minus 1 upon 1 minus e power minus t by mu Z power minus 1. This is the y of Z by y set point of Z. Already we know that what is digital controller, d of Z equal to 1 by HGP of Z. 1 by HGP of Z. Numerator y of Z by y set point of Z. That this you have to write, divided by 1 minus this you have to write. If you take LCM, this term getting cancelled in the numerator, and denominator also, instead of 1, this term will come in the denominator term. Therefore, this is the controller, generalized controller for Dahlin's method. So from here, what and all the design parameter, mu, not k. K is actual dead time plus 1, TD plus 1. K equal to KT equal to KT equal to KT must be greater than TD plus 1 sampling period. TD plus T, 1 sampling period. That way we selected. That's why this is not a design parameter. The design only design parameter is mu. Wherever you find mu, you can select. And the Dahlin's controller, it depends upon the mu. You can select, you can choose the mu value to design the Dahlin's controller. If you choose a large value of mu, you will get a sluggish response. If you select a small value of mu, the response will be smarter but oscillatory. So you can select the mu, depends upon the type of response you want. Then second is the system is physically realizable. The controller is physically realizable. The dead time is not larger than k plus 1t. What we are assuming while designing the controller, the KT is greater than TD plus 1. So KT must be deadbeat. Within 1 sampling period, we want the response should settle. That's why large controller output will generated within that 1 sampling period. So overshoot will be large, and then because of that, oscillation will be more. That we can avoid it because we designed the controller for dead time plus first order response. That's why this can be significantly reduced in Dahlin's. That is the second advantage. Then we'll design the controller for Dahlin's versus deadbeat. Let us see. Yesterday we have seen how to design a Dahlin's controller. Let us design Dahlin's and deadbeat for a particular process, and we will demonstrate that. So GP of S equal to 10 upon e power minus 2s 0.2s plus 1. That is taken. So sampling period equal to 1 second. then the process dead time, suppose the process dead time is 2 seconds, here 2 seconds. Therefore, the deadbeat controller will be 1 by HGP of Z, 1 by HGP of Z multiplied by Z power minus 3. Why minus 3? No dead time means Z power minus 1. Dead time is 2 sampling period. That's why Z power minus 3. 1 minus Z power minus 3. That is written here. So if you do like that, for this system, this is the controller. This is the controller. 0.99 Z power minus 3 upon 1 minus 0.01 Z power minus 1. This is the controller. Deadbeat. 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 We are going to compare deadbeat and Dahlin. So for that, we designed a deadbeat. If you design this, you see, further simplify. If you further simplify, you will get this is HGP of Z. This is HGP of Z. You got HGP of Z. You got. Then if you substitute in the HGP of Z in this, you will get this. So this is controller based on deadbeat. This is the controller based on Dhalins. In that, what we assumed, mu equal to 2. Mu equal to 2. And dead time we assumed is theta equal to 3. We assumed. Already I said theta you should assume TD plus 1. TD plus 1. That's why theta is assumed as 3. So if you assume like that, the dead time theta is assumed as 3 seconds, and this is mu is 2. For that, if you design, this is the controller, 1 by HGP of Z multiplied by this we used, this formula we used. This formula we used. What is that formula? This is we used. There, the mu is substituted as 2, K is substituted as 3, and T is substituted as sampling period. T is substituted as 1. If you substitute all this, you will get this controller. This controller. This is the controller we got. If you simulate this, if you simulate the deadbeat, you will get large overshoot. And if you simulate Dhalins with mu equal to 2, you are getting better response. You see that? If you choose mu equal to 2, this is the response. If you choose deadbeat, this is the overshoot and the oscillation. This is the response. So in the here, if you choose mu equal to 10, very sluggish response. Very sluggish response. This is mu equal to 10. If you choose mu equal to 1, smarter response. If you go on reduce the mu, it will approach deadbeat finally. It will approach deadbeat finally. So mu is the design parameter. We can select mu such a way that the response is good, acceptable. Now let us move on to the ringing. That is the topic today we are going to see. Ringing means the controller output itself oscillates. The controller output itself oscillates mean between 2 sampling periods. Between 2 sampling periods, first sampling period, the controller output is positive, means the next sampling period it will be negative. The third sampling period it will be positive. That is called ringing. Before seeing that, what is the D of Z? What is D of Z? It is the polynomial ratio of 2 polynomials in Z. That is D of Z. You see in the previous examples what you got while designing deadbeat. You see that this is numerator polynomial and denominator Z polynomials are there. So D of Z will be polynomial in numerator and denominator. Both have some polynomials. So this is the numerator polynomial of the given controller, and this is denominator polynomial of the given controller. The denominator roots of denominator polynomial is called poles of the controller. It should be stable. It should be stable. Otherwise, even though the system is stable in open loop, in closed loop also it is stable, but the controller you designed is an unstable, means definitely the final response will be unstable. That's why the controller we designed must be stable. That is one point. Another point, let us assume that we are finding the poles of the controller. One such pole is P. So we factorized the controller. We got one such factor is 1 minus e power p z power minus 1. Or this is the controller. Let us assume only one factor it has. One pole controller, let us assume. If this is the controller, means let us realize this. D of z is equal to C of z by E of z. This is the controller transfer function. This is the controller transfer function 1 by 1 minus p z power minus 1. So Cn minus P Cn minus 1 E of n. How we got this? You cross multiply these two. C of z, if you cross multiply this, what you will get? C of z multiplied by 1 minus p z power minus 1 equal to E of z. If you write this in time domain, before that let us multiply inside. E of z minus p z power minus 1 E of z equal to, sorry, C of z, this is C, left hand side is C, controller output C, this is C of z, then E of z. So if you write in time domain, E of z is E of, so controller output is C of n minus equal to P of n minus 1 plus E of n. You will get this is the control output, C of n minus 1. So what is the meaning of this? P multiplied by previous controller output. C of n equal to present controller output equal to P multiplied by previous controller output plus error E of n. This is the realization of this controller. Realization of this controller. That is C of n equal to E of n plus P C of n minus 1. Yeah, let's remove this. So this is the controller output. C of n equal to E of n plus P E of C of old controller, C of n minus 1. Let us assume that P equal to 0.9. Then what you will get? C of n equal to P equal to C of E of n minus 0.9 E of C of n minus 1. C of n minus 1. So minus sign here is there. Or you can put P equal to plus 0.9 also. It depends upon the location of pole. Suppose if you draw all poles of the controller, it should be within that unit circle. Then only it is stable controller. If the two poles controller means here, one pole controller means must be on the real axis, but here, or it may be here. If P is plus 0.9, it will be here. Plus 0.9 means it will be here. That is Z plane. Z plane. This is the real axis and this is imaginary axis. And if it is plus 0.9, pole will be here. Minus 0.9, then pole will be here. Two cases let us consider. If it is in the left hand side, what will happen? If it is the right hand side, what will happen? That we will see. it is in the left hand side, what will happen? Right hand side. So we what for that, what we have to do? We have to substitute this in this. Let us assume that initially the control error is 1. Yeah, impulse error we got. Substitute what you will get. Let us assume that initial controller output is 0. Previous controller output is 0. What you will get? Initially the error is assumed as 1. For impulse input came. Impulse error came. That's all. After that it is 0. After that it is 0. There is no error. Input. But what happens to that controller output if P is negative? If P is negative, 1 minus 0.9, plus 0.8, minus 0.7, plus 0.6, minus 0.5. Like that, the controller output is oscillating between positive and negative, but it is decreasing. Stable controller, that's why decreasing. 1, 0.9, 0.8, 0.7, 0.6, 0.5. Finally, it becomes 0. That is different. But it gives positive value and negative value. Here, if you see P equal to plus 0.9, it is also stable controller, decreases 1, 0.9, 0.8, 0.7, 0.6, 0.5. It is also come to 0. Without any oscillation, it comes to 0 if P is positive. That's why if the pole of the controller must be on the right hand side, that is plus 0.9. If it is in the left hand side, minus 0.9, then stable controller, but it will give a ringing effect that is given in the waveform. If you plot the controller output, if it is minus 0.9, it oscillates, it gives positive value, negative value, positive value, negative value, alternatively. That's why it will come to stable point after oscillations. Here P is minus 0.3. Then also it oscillates, but not this much amplitude. So if P has smaller value, then the amplitude of oscillation reduces, but oscillation is there. On the other hand, if you select P equal to plus 0.9, it decreases like this. If P is plus 0.3, it decreases like this. So to avoid ringing effect, after designing controller, we have to factorize the denominator and check the roots of we have to check the roots of the controller. The roots are positive. Roots of the controller, we have to check the roots are positive, then there is no ringing effect. Otherwise, you will get a ringing. Then let us, this is the ringing. These are the desired poles. It should be on the right hand side, not on the left hand side. This is not ringing poles. These are all ringing free poles. So the poles of the controller must be on the right hand side. Next, it has positive pole, positive 0. No need to worry about 0. Only we have to see the poles. Here, positive pole, positive pole. This is negative. So 0.6 is that equal to 0.6 is the negative pole. Minus 0.6 is the negative pole. That's why it will give ringing effect. It will give ringing. How to remove this ringing effect? For that, one method is replace this by its steady state value. Steady state value, how we can find what is the term? 1 plus 0.6 z power minus 1. In this, substitute z equal to 1. You will get 1.6. You will get 1.6. You will get. Replace this by 1.6. That's all. Replace this by 1.6, and instead of this, you put in the numerator and denominator. What you have to do is if you multiply the numerator by 1 plus 0.6 z power minus 1, then automatically this and this will getting cancelled. But controller is not correct. So to compensate for its steady state magnitude, you put z tends to 1, z tends to 1, z tends to 1 of in a limiting case. Limit z tends to 1, you write 1 plus 0.6 z power minus 1 in the denominator. Then this is steady state value. Steady state value. Z tends to 1. Z tends to 1. 1 plus 0.6 z power minus 1. So these two getting cancelled and this will be there. So what the final controller, instead of 1 plus 0.6 z, we are substituting 1.6 here. So you will, the controller will be ringing free. Controller will be ringing free. Now let us see some simulations. Let us once again see what is ringing. Ringing means if after designing the controller, we have to check the poles of the controller. Thus must be within that unit circle, then only the controller is stable. Once the controller is stable, we have to check the location of poles. If any poles on the left hand side of this unit circle, then these poles will exhibit ringing. These poles will exhibit ringing. So replace this by substitute. You check that, you see that if the pole is on the right hand side, if the pole is on the right hand side, P is negative value. So pole is on the right hand side. Pole is on the left hand side. 1 plus 0.6 we have taken that example, z power minus 1. If you check, the pole will be on the left hand side here, 0.6. But within that unit circle, stable. But if you inject impulse input, it gives alternate positive and negative values. That's why it oscillates. On the other hand, if you select the 0.6 on the positive side, plus 0.6, then you are getting no oscillations. Both are stable controller, but it doesn't give controller output is not oscillating here. Here it is oscillating. That's why this is not acceptable. So if the controller has negative side poles, then it oscillates. Even it is smaller pole, it oscillates, but it quickly damps out. But anyhow, oscillation is there. On the other hand, if it has poles on the right side, you see that the right side of the unit circle, if it is smaller, quickly damps out. The controller comes steady state. If it is larger, it takes time, but anyhow, no oscillations. That's why these are all desired poles, right hand side, and the left hand side are not desired pole, even though this is a stable controller. How it can be removed? It can be removed. The ringing poles can be removed by replacing by limiting case. So 1 plus 0.6 can be replaced by limit z tends to 1 plus 0.6 z power minus 1. If you substitute z equal to 1, you will get 1.6. So this term is replaced by 1.6. So ringing effect is eliminated. You see that this is negative feedback. A step input is given. Negative feedback. This is the controller for Dhalins. That system we take. The system we have taken is yesterday we have seen, that 1 by 0.2 s plus 1. Yes. 10 upon 0.2 s plus 1 is the system taken. First order system. Gain is 10. Time constant is 0.2. 10 upon 0.2 s plus 1. That system is taken. And transport delay is taken as 2 seconds. For that, we designed a controller with mu equal to 2, and this is 0 order hold with the sampling period 1. Yes, for this we designed a Dahlin's controller. This is the Dahlin's controller for that with mu equal to mu equal to 2. For that, if you design, you will get the response like this. This is the response. So it is like dead time and first order response, like that you are getting the response.